Hi, Anna. I'm gonna just kind of get on here and show you what's going on with this. Maybe that'll be easier than trying to type it out and explain it. So, again, I am so sorry that I never got back to you. I just looked and I see the message is right there. I even started and never came back to it. So, um, if I ever do that again, just feel free to just keep emailing me. If I don't get back to you right away, it's probably because I forgot. So on here you are looking at this was specifically to look at the different polarity of bonds. These are all going to be covalent. Well, not all of them, I shouldn't say that. So some of these are going to be covalent bonds, some of them will be ionic bonds. So if it's between a metal and a non-metal, it's going to be an ionic bond. And when that's the case, you're going to be transferring electrons. Okay, so if I do, I don't know, let's do sodium and chlorine. I'm just clicking them and dragging them up there, right? So if we look at this, you're looking at kind of like its radius here. So then if I press play, well, actually, let's try on some valence electrons there. Okay, so this is the atomic radius. So chlorine has a tighter radius because the nucleus has a stronger attraction to its electrons. So it's going to be more difficult to remove valence shell electrons from a chlorine atom. So anything on the right-hand side of the periodic table, they want to keep their valence shell electrons. So there's this strong bond coming from the nucleus all the way out to the edge. So that's why these rings are closer together than on this side. So on this one, for your sodium, you can see that it has the same number of rings, but they're a lot further away. That's because there's only one valence shell electron out here, and sodium would be fulfilling its octet rule if it loses this electron. So it has a larger atomic radius because it's less strongly bonded to its outer shell electrons. So anyway, that's kind of just explaining the what there. So if I have these two, we know that chlorine would have 7 valence shell electrons and sodium would have 1. If we Let's see if it shows your electronegativity. There we go. Okay, so we can turn this on and see the electronegativity difference. So if you look up these on the slides, like right around slide 32, I think, there's an electronegativity chart. So you could find the difference, the electronegativity difference between the two atoms to figure out whether it was polar, nonpolar, or ionic. So in this case, you could look at this. It just tells you that the electronegativity difference is 2.1. You would find that just by subtracting, right? So you have chlorine is 3.0, sodium is 0.9, so 2.1. That's going to tell you that it fits into this category of ionic bond. So if we hit play, oh, there we go. Okay, so you can see that chlorine accepts the electron from sodium. So sodium lost its third ring. I don't know if you saw that, kind of happened fast. So if we go back, so sodium has 3 rings with this one on the outside. So if we hit play, that electron's being transferred over to chlorine, right? So now chlorine has a satisfied octet rule, so does sodium. Sodium's going to have a charge of +1 because it got rid of one of its electrons, and then chlorine becomes a -1 because it accepted an electron. So we're going to drag these bonded atoms over into the correct category. So this one was ionic, so we're just going to stick that one in there. So depending on what the question's asking for, that's how you're going to be doing that. So if we have oxygen, and let's just bond it with another oxygen. Okay, so this is what we would call a diatomic molecule. They're going to double bond together. Each of these have 6 valence shell electrons. They each need 2 more. So if you look at the electronegativity difference, it's 0. They're exactly the same. So 3.5 minus 3.5 is 0. So if we look over here on the right-hand side again, we're going to be able to identify that this is a nonpolar covalent bond because the difference in electronegativities is less than 0.4. So if we hit play, it's going to show that these are sharing. Okay, so oxygen is one of your 7 diatomic molecules. So it is sharing, they're both sharing these 2 electrons here. We already just figured out that it is nonpolar, so we'd stick it in there. So again, you would just keep on going with this until you find one that is going to be, let's see if this one would make it. Yeah, so zoom out a little bit. So if I stuck together carbon and some chlorines, it's automatically going to add in the extra atoms of chlorine to satisfy carbon's octet rule here, because this is how it would actually bond. So you'd have like CCl4. So the difference in electron activity between carbon and chlorine is 0.5. That's going to fall into the polar covalent. And so if we hit play, it's going to show that they're sharing. Okay, so this is different than the first one that we saw where chlorine accepted the electron and sodium was transferring it away. These aren't giving them up, they're just sharing them. So we know that it's going to fit here. So that's what you're doing on this page. You're just like dragging these atoms up and making different types of bonds. And then here, if you click this box, this is just giving you an example of what a polar bond would look like. So polar bond just means this is a covalent bond and they're sharing their electrons. You can see the electrons, but obviously one side has like a stronger hold on those electrons. Okay, so if you look at it, the left-hand side here has, I don't know if you'd call it access, but it has more pull on those electrons, so those electrons are more likely to be on that side of the compound rather than on the other side. So if we close that, this one's going to show you a nonpolar molecule where you can clearly see that they're equally sharing. So nonpolar, they're equally sharing. Polar, they are not equally sharing. So if we go across the top here, molecular polarity and then intermolecular forces, I'm just clicking on these to change them. So I think, I'm not sure if I cut out part of this or not. I can't remember off the top of my head. But if this isn't part of your instructions on the lab, then you can ignore this. But so here we have, oops, there we go. So here we're going to have, show those again, an electric field, right? So if we turn that on, you can see how it's orienting itself, right? So the positive and negative are going to be attracted to one another, and then the same on this side. So you can see by just flipping this around, one side is obviously has a larger charge. So you would pull this into the polar category. So if I picked another one, let's do nitrogen, turn on the electric field, nothing happens, right? Because they're equal. One of them is not more positive or more negative than the other side. So we'd drop that in there. And then for your intermolecular forces, let's see. Stick these on here. This is just showing you how your polar molecules and nonpolar molecules would behave near one another. So for a intermolecular bond, that's a bond between two molecules, right? Between nonpolar molecules, the molecules have to temporarily become polar, okay? And that has a lot to do with what we were just on the other tab. So with these two, you can see that they are equally balanced. Neither side is positive or negative, which means they're neutral. They're not going to want to be attracted to one another if they're neutral. So in order for them to bond together intermolecularly, these have to temporarily shift so that they do have a positive and negative end. Whereas on this side, you have your intermolecular bonds just naturally form because you do have the positive and negative sides to that. So if you are dragging your molecules up here, you're going to drag another molecule. I don't think it matters from which one. And then you hit play. You have several different molecules floating around. It's just going to show kind of how or where they would bond together. So I feel like this is not part of the assignment because we didn't actually talk about this yet with dipole and London dispersion. So if this is actually part of the assignment, you can ignore that. So what you'll focus on is your bond polarity and then the molecular polarity. Let's see. This down here with the assessment questions, you're not doing that. You don't need to do these. They're just like, they're there. It's an option, but you don't have to do those. So if I go back here, let's see if I look at this. Let's see if this takes me to the right tab. Okay, so I switch it. It should be showing you this tab now. So this is the Gizmo. I think it was a Google Doc, so you can just type right in it. But basically, you just have some situational questions to answer here, kind of a warm up of like, what do you see happening? Try to be specific with the electrons because that's really what the focus is. And then you are looking at the bond polarity, which was the first tab. So this is a difference in electronegativity, whether it's ionic polar or nonpolar. And then the molecular polarity was the second piece of that. So when you get down here, if this is in here, page 6 and 7 for activity C, you can ignore that. Okay, so you can just ignore this part because it's like dipole forces and London dispersion forces, and we have not gotten that far. So hopefully this is helpful. Let me get back on here. Okay. So hopefully this is helpful for you. And sorry, this is kind of long, but please let me know if this was not helpful, and I can figure out another way to explain it, or if this was just not at all what you were talking about, then sorry to waste your time on a Friday afternoon. So let me know if it's helpful. If it's not, we'll figure out what the problem was and address it. So let me know.